Welcome everyone to the Maui Institute for Astronomy. I'm Dr. JD Armstrong. I'm the Maui Technology, Education, and Outreach Specialist. And one of the things I do is put together these talks. And so when I realized, hey, we need a speaker for January and Russ is in Hawaii, I very quickly came to an obvious conclusion that we needed to drag him over here and have him come talk to you guys. And he is going to be talking about small telescope research communities of practice. A little bit of background on Russ. He is so Dr. Russ Genet. He started out literally as a rocket scientist. So when you talk about rocket scientists, this is the guy. And he was working in aerospace research and development as a supervisor or chief scientist at several government labs for many years. And then he kind of started getting more and more into astronomy, kind of drifted in. Am I getting the story right?
That's it. Yeah.
Okay, great. And he is one of the pioneers of robotic telescopes, of automated telescopes. He's co-authored over 100 papers, and he is currently a research scholar in residence at Coosa College, and UH also has put him on the roster there as their faculty, if I understand
That's
correctly.
right.
Great. Well, let's give Dr. Genet a nice Maui welcome.
Well, thank you very much, JD. And I've been working with JD for at least 5 years now, and we had a very nice conference here at the Institute for Astronomy in Maui. Steve, when was that? That was what, four years ago? Yeah, on double stars, and we had about 40, 50 people. Totally filled this room up here, and it went well. Okay, so what I'm going to do is talk about small telescope communities of practice, and just three things that I really want to talk about, and I want to leave room at the end. And Steve, do you have a watch there? I'll ask you occasionally for a time hack. So what time is it? 6:41. Okay, and we want to definitely keep this under an hour. You don't want you to stay up too late. So I'll ask you for a time every once in a while. At any rate, so three things. We're going to discuss just briefly what are communities of practice. And then I want to give you two examples of communities of practice in astronomy that I've been associated with. And one had to do with photometry and automation of telescopes and observatories. And the other one is a student-centered research community of practice. And we were actually talking a little bit about the lobby, this seminar where where students do actual astronomical research. Okay, so the first thing is, what is a community of practice? Well, a community of practice is essentially they're informal groups that work together to produce something, to learn something new, and they're kind of what humanity's been doing for eons. So actual schools where you went to school and teachers taught you, that's really recent, just the last 5,000 years or so. And prior to that, you just learned by joining a group. If you were going to learn basket weaving, you'd sit down with the other basket weavers, and you'd be the junior basket weaver and learn the ropes of how to weave baskets. Well, but any human endeavor you want to. So who's the robotics instructor? Okay, I mean, you have a community of practice in doing your robots, don't you? Yeah. And okay. So at any rate, the basic idea is the experienced ones teach the newcomers the ropes how to do it, and there's lots of things about a community of practice that you won't learn in school. So there's kind of unwritten rules of how you do things, and so science is no exception. So if you're going to be a scientist, you go to school, you learn about different topics of science, but when it comes to doing the actual scientific research, the normal way to learn is you go to grad school and you do research, and they you learn the ropes from the professors at grad school doing research. Well, you don't have to wait to grad school to do research if you want to do it younger. But at any rate, so there's a communities practice is a one area of social learning theory, and so the psychologists have developed the social learning theory. Okay, so the first community of practice I want to talk about was uh, professional amateur collaboration in the development of photometry and automation of telescopes and observatories. And so it's something that I was involved with. I started out while I was in grad school. I had a little extra time and wanted to do some actual hands-on science. And so I built a telescope and a photometer. A photometer is something that measures the intensity of light. And so the kind of thing I would want to use a photometer for is, for instance, is the varying light from stars. So some stars actually pulsate. They get larger and smaller. They get brighter and dimmer. There's other stars that have that they're a binary, like we were talking about. And these kind of binaries, one binary star actually moves in front of the other, blocks the light, and then moves out. So you get this big dip in the light. There's some stars that have spots on them, big dark spots. And as the spot rotates around, the light will dim. And so that's the kind of science we're doing. Computers had just come out. The very first Apple computer in the late 70s was about $2,000. And then there was the Radio Shack computer, which probably almost anyone here have heard the Radio Shack computer? Jeff and JD, they're showing their age. Anyone else? The Trash 80, good man. So this is a 1979 Trash 80, and I used it to analyze my data, but astronomy is not unusual this way. Almost any area of science you go into as a researcher, there's fun things, but there's always dog work involved. And so astronomy, doing photoelectric observations back of variable stars back in those days, you would find the star you're going to observe, and you would put a filter in. You would start a strip chart recorder, and it would record, and then you would move it off the star to get some background, and then you'd move it to a comparison star, and anyway, you go through this very mechanical sequence over and over and over, and so it's boring. And so, of course, I started thinking about, well, you got these new computers, maybe instead of the strip recorder, we could get to log the data for us, and we don't have all this mess of paper. And then, well, maybe I could have the computer prompt me. Let me see. Is this the laser? Yes. So the computers in my study, where it'll stay warm, they weren't very environmentally rugged. And so here's the computer monitor out here, and I've got a little keypad, and the computer would tell me what to look at next. And so I move the telescope there and start recording the data. And at some point, you're standing out there listening to the cows and a little bit of music or something, start thinking, well, if the computer can do this, why not have the computer change the filters? And, okay, so we get the computer to control stepper motors, and then, so it's kind of gathering the data automatically. You get it on the star, and it goes through its functions. But then, of course, you start thinking, well, I could go to bed and go to sleep if I just got the computer to actually run the telescope. So we'd been developing, this was, to try to understand, to try to do something new in science, you want to get with other people. And so this was actually our first meeting of group for photoelectric photometry. And it was at the Dayton Museum of Natural History, about a dozen of us. 3 years later, we had a big group, and so we had developed a really good community practice. A combination of amateurs, many of them that were engineers, students, and professional astronomers. It was a real eclectic group. It was just lots of fun. And I started writing books on the topic. This was probably the first book on control of devices with a microcomputer, and this is how it worked. So we didn't have electronic CCD cameras in those days. We had what's called a photomultiplier. It's essentially a 1-pixel device, and we would move the telescope to where we thought the star was, but it would never be, it'd be close, but not quite there. And then we would move the telescope a little bit one direction, move it down, and just step it around in this square spiral search. And each time it would stop, is there a star there? And no, move on. So when it finally find the star, then we had some moves where we would use the center of the star, and then we would make our first measurement. And we go through, there was actually 33 different measurements. It took it about 11 minutes for this robot to go through and make the measurements. And once we got it going, I went up and briefed the National Science Foundation, and they asked us if we'd like some grant money, and we said, well, twist our arm. And the Smithsonian offered us a spot at Mount Hopkins, which is kind of halfway between Tucson and Nogales, the Mexican border. And it's the home of the multiple mirror telescope up on the ridge. It's now a 6.5 meter telescope, but back then it was a multiple mirror telescope. And our building had a big roll-off roof. We modified it a bit. And so we started out, this was my telescope I brought from Ohio, and it was the first telescope up there. And we added telescopes over the years, and I ended up with 7 telescopes. And we had meetings every winter at the Lazy K-Bar Guest Ranch in Tucson in the middle of February. And the astronomers flocked to it. We always filled it up. They'd get a tan laying around the pool, and we'd ride horses, and they'd always come up to the observatory. At any rate, that was essentially a decade's worth of conferences was what launched the robotic telescopes and the robotic observatories, of which a great example is the 2-meter telescope up here in Haleakala. So that's a wonderful robotic telescope. This was a 1985 book. It's a 1995 book. This is a 89 book on robotic observatories. And I retired from being the director of the Fairborn Observatory in 1991, but the observatory kept going. And in 92, Bill Barucki at NASA Ames, he and I did a paper suggesting that you could detect exoplanets with transits that we talked about a little bit earlier, with an exoplanet going in front of the sun. And we could use robotic telescopes to do this, to get a network of robotic telescopes around the Earth. So we approached NASA, and they did not like the idea, actually. But Bill Barucki kept at it and proposed a space telescope, which NASA did like, and it's called Kepler. And it's discovered something like, I think, what's the latest count? About 3,000? Yeah, so that's the main, most of the exoplanets we know are now the transit method. But this light curve of an exoplanet, it was discovered by the telescope at the Fairborn Observatory, so I designed to build a telescope, but I had retired quite a few years earlier. And David Charbonneau at Harvard also observed the same one. So they were 2 papers in the Astrophysical Journal, back to back, on this first exoplanet transit. That often happens in science, where discoveries, when the time is right, you have more than one person discovering something. Okay, so that's the first example, and just to kind of summarize, the key thing here is that this was a group of amateur and professional astronomers and some students that worked together to develop the technology of small robotic telescopes. And it was primarily led by the amateurs, and most of them were engineers. And so, and kind of one of the jokes was that, the professional astronomers, usually on a, when you get these amateurs and professional astronomers together, the professionals are the ones that really know what's going on. Well, in this case, it was the amateur engineers that was going on. So they, in a way, they were the real professionals. But working together in this community, and it was totally voluntary. We'd have our meetings and exchange things. That was how things got done. So the second thing I want to talk about is the development of a student-centered research community of practice. And so this was the original idea, and it was back in 2001. I was in Arizona. My last regular full-time job was as a research supervisor at a government laboratory in Mesa, Arizona. And so I retired in Arizona and was teaching part-time at Central Arizona College. They had a small campus at Superstition Mountains. And the dean there was a good friend of mine, and I was talking with him at lunch one day and says, I'd like to try to see if we could get students to do actual published astronomical research. And he said, sure, Russ, do whatever you want. And so this was our first class. There was actually 9, so we got 1, 2, 5, 6 of the students here. So we're missing 3. One of the students was actually my wife, Cheryl, who was teaching philosophy at that time. At any rate, so this is the original idea, is as really a supplement to lecture courses and lab courses, of which students take a lot. Let's just see what they can learn by actually just doing science. And JD, what's the kind of term, the Hawaiian term you were mentioning? Which means the knowledge is in the doing. And so we're going to have, that's a good, nice Hawaiian term there. So, and I think there's lots of truth to that. And so the idea here was not to have, and this works, it's a great thing to have students mentored by, a student or two, a small group of students will work with a professor all summer doing research. And, they just they learn the research that way. Well, we decided we want to take a different approach where the students would actually plan the research out themselves and then run the show. So the students would be in charge. And something that it took us a while to really understand was that it's good to have student teams with lots of different talents. So for instance, you would think that in astronomical research that what you would want is students that are really good at math. Maybe they have some background in physics, and of course these days you're really good in computer. But guess what's the most important talent for this research seminar? Is what? I still didn't understand. Oh, teamwork. Yes, absolutely. Teamwork's very important. But in terms of an individual thing, is it math or physics or imagination's important? It turns out that writing is the most important because published papers are the product, and so the students that write well actually end up being the most valuable team members quite often. But so you want different talents on the team. That's helpful. And we found that some students have lots of time to work on it. Other students are real busy doing things. They don't have so much time. And, in normal classes, you try to get all the students to kind of do equally, and if some students can't contribute. But in science, and we found that really what you want to do is follow all the rules in science. So I've been my whole career was essentially as a science research supervisor, so I've seen lots of projects succeed, lots of fail too. And the typical science team, you'll have some of the scientists that have plenty of time and the project's real important to them and they kind of lead the project. You'll have some other scientists that's just doing some piece. They're contributing their little piece. They've got other projects they're doing, so they don't spend as much time. And you'll have a scientist that starts out doing a lot and they get another job and they're gone. And so you have unequal participation, and that's the way of science, and it works well on a research seminar. It doesn't work so well in a regular class. So at any rate, you have to follow all the usual rules of science, and that includes science. Ooh. Oh. the in one of the key rules of science, if you do research, you really have to publish it. If it doesn't get published, in a way, it's not science. You know, if the data never gets out there, the results never get out, and it's also important to present results publicly at a conference if possible. So that's kind of the original idea, and turns out it worked well, and we refined it over the years. We originally did research on eclipsing binaries and pulsating variable stars, and it took a long time to gather the data. And so it would be many nights, students out at my observatory, and they would eat out the refrigerator, and and you know, about the semester would be over halfway through, and we're finally getting our data and starting to reduce it. Well, the problem was we ran out of time at the end of the semester to write and rewrite the paper, and so I had promised the students that we were going to have a published paper. The semester ends, the students disappear. Guess who has to finish it up? Well, that's not the idea. You want the students to finish it up. So we found that by observing double stars, you could get all the observations you need in one evening. It was essentially fast and easy observations, and that way you could spend a little time, and the reduction was easier, and you had plenty of time to work on the papers. And so since the Montessori team maybe we're working on double stars with the idea, I'll tell you just a little bit. How are we doing on time, Steve? Half what? Oh, 45. Oh, we're fat, dumb, and happy. Okay, so looking over here, we're going to talk about Johannes Kepler's 3 laws. So Kepler's mathematician in the late 1500s, and sometimes people think that his contribution is really kind of the beginning of modern science. But here's what he did. He, along with Copernicus, realized that the sun was the center of the then known universe, and so Copernicus had assumed, like the Greeks had, that this is the sun. They assumed that the planets went around the sun in a perfect circle at a constant velocity. Okay. Well, when they started getting better observations and trying to match it, it didn't quite fit. And so Kepler had a big data set that actually of the position of Mars with respect to background stars. And so he analyzed that, and he says, well, you know, this idea that the Greeks had that it's a circular orbit, maybe that's not right. So he tries an oblate orbit, tries different orbit, and he finds that an elliptical orbit works quite well. And so this is Kepler's first law. And an ellipse has 2 foci, and the sun is at 1 in our system. What's at the other foci? Nothing. This is a trick question on introductory astronomy lectures. Okay, so that was his first law, but then it still wasn't as good a fit as he wanted, and so he got thinking, well, if the orbit's not circular, maybe the planet doesn't go around at a constant speed. Maybe when it's further away from the sun, it goes slower. and when it gets in closer, it goes in faster. So it's kind of like that. And and he realized that, so let's say this is 1 month. So when it's in close, it's moving faster. When it's out further, it's moving slower. But he did a little analysis, and he realized that this area here in blue is the same as the area in green. So the planet, his second law is that a planet sweeps out equal areas in equal time. And so this applies also to double stars. And then he realized empirically, this is a plot of the period versus essentially the semi-major axis of the orbit, kind of the size of the orbit. And here's the equation form. The square of period is the cube of the semi-major axis, how big the orbit is, divided by the mass of the two objects. And you can plot this so you can see if you do a log plot. Here's our different planets, and they really do fall on a straight line on this. So the connection between, okay, aha, there we go. So the connection between Kepler's three laws and double stars is that if you get the orbit of a star, so pretend that's the bright primary star, and then these are observations over time of the secondary fainter star, and it's going around in this direction. So this is getting out in orbit. You can get the period, and if you know different positions here, you can apply Kepler's second law, and if you know those two, then, and you know how far away the star is, you can get the angle, what the semi-major axis is, then you can figure out what the combined mass is of the two stars. And so in astronomy, in astrophysics, the one of the most sensitive things that determines the life of the star is the mass of the star. Massive stars have hot nuclear furnaces in the center, and they go through their lives real fast. Real small stars, the fires are barely lit, and they can last trillions of years. And so determining the mass of a star is really an important thing, and essentially the only way you can do it really accurately is with binary stars. So we want to find new binary stars, and we want to keep track of them over time so we get the orbits. We get the period. We can apply the second law and get the masses of the stars. So this is an important thing. And we found, so we started the seminar using an astrometric eyepiece. So this is an eyepiece just like other eyepieces you put in a little telescope. And the difference is it has a laser etched reticle, and it's essentially just a ruler, a scale here, and a protractor. And so when you look through the eyepiece, and you got a double star up there in the sky, you see this red protractor around the double star, and you see this ruler, and you can rotate the eyepiece until the ruler goes through the two double stars. You count the tick marks on the ruler to get the separation between the apparent angular distance between the two stars, and you can turn the drive of the telescope off, see where because stars drift east-west, right? And you see where that goes on the protractor, and that'll tell you the position. So that and the date that you make the observation, you got the time, you got the separation, and you got the angle of the star, and those are what you need to do the plot. The date is around this way. This is the angle, and this is the separation. And so this costs less than $200. So and nothing to go wrong. And so that's what we started using, was an astrometric eyepiece, making these observations. This was our first class. It was actually held at a high school, Cuesta College, and so these are many classes over the years. and the seminar started expanding. So here's, there you are, Steve. And so, so how long ago was that, do you think? 4 years ago. This was up at we had a program with the University of Oregon that I did. So we had 4 summers in a row where we had a little summer camp. And they had a 24-inch Bowler and Chevins telescope, and students came in, selected double stars observed, made their observations. They reduced the data, wrote their papers while they were up at the camp. We had external referees standing by on the internet, sent the papers. The next morning, they get them all marked back, all marked up. This was one we held up at the Oregon Star Party. Like I say, this was here in Hawaii. This was a regular introductory astronomy class then in the summer, and had a bunch of sharp students. I says, instead of kind of doing the regular term paper and so forth, would you like to do research? How many? And essentially the whole class said yes, and we did three papers. This was the last day of class, submitting the 3 papers to the Journal of Double Star Observations. So this is a typical. It's not typical in that it had a single author. Almost all the papers are multiple authors, but this is maybe the 3rd draft, and so these are my markups. And this was about 5-page long paper at that time, and this is the most difficult part of the seminar. And if you all at Montessori do this project over the next what'd be about 4 or 5 weeks, that'll be the hard part. We'll be doing the paper, so we'll want to take on something really kind of fast and easy, give ourselves plenty of time to write and rewrite and rewrite the paper. But the papers all get squared away, so this one got boiled down from 5 pages to 2, and all English checked and squared away. So I got interested in how could you increase the scientific value of our observations? How could we, with the astrometric eyepiece, the double stars had to be fairly bright and fairly wide apart. And now, Steve, how faint can you observe visually up on Haleakala? They go down about 11th magnitude, 12th, and of course that's one of the world's best observing sites. And how close a double star can you observe? Oh wow, that's good. Is that on an exceptional night or? Yeah, okay. And now the close for double stars are the same distance from Earth. The closer the double stars appear in the sky, the closer they're actually going to be. And so the closer they are, what happens to the orbital period as they get closer? Is the orbital period going to get longer or shorter? Okay, yeah. If they get shorter, they're going to speed up. And so there's more scientific interest in ones with short periods because, in our lifetime we can nail them down because there's some known binaries. Their orbital period is millennia. So one of the things that we were interested in was how can we observe double stars that are really close together. It turns out there's an approach called speckle interferometry. And so this is a visit. When we were out in the lobby, I mentioned my star student, Joe Johnson. There's Joe Johnson there. And we're at Kitt Peak. This is actually in a telescope. So this is the back end of a telescope. It's a 4-meter telescope. It's so big there that it's called the Cassegrain cage. And so the light's coming down here, and this is a speckle interferometer, a pretty large instrument. This is Brian Mason at the Naval Observatory. So when you do the Washington Double Star Catalog, so how many have looked at the Washington Double Star Catalog? Okay, quite a few students. So Brian Mason and Bill Hartkoff, those are the guys at the Naval Observatory that do the Washington Double Star Catalog. Anyway, this was maybe 7 years ago, and so I got interested in speckle interferometry, And but to do it, you need a high-speed, low-noise camera. And at that time, they were $14,000. And so I talked to the company Andor in Ireland, made them. They said they would sell me one for half price for only $7,000, and a demo model that had been out. And so I got put in a grant request to the American Astronomical Society, of which I'm a member, and they said, okay, we can go 7,000, and so we glommed onto a camera, and they're really quite magic. They very low noise, and what you do is you take, instead of taking one image with an exposure of maybe 10, 20 seconds, something like that, you take 1,000 images in about that same amount of time. And so you get a gigabyte of data in seconds. And what it does is, the problem is that like when Steve's up there on not the best night, the, the stars jiggling around, okay? And so if the double star is pretty close together, it's going to jiggle around, be hard to see. And if he's taking a time exposure with a CCD camera, it's going to smear. So instead of getting a double star, you get this blob. And but if you take a real short exposure, you can see the two stars. You take another short exposure, it's jumped over here, boom, boom, boom. And in fact, as the light comes through the atmosphere actually breaks it up. It's got like a bunch of little lenses. And so you get a bunch of images of the double star. And these are actually called speckles. So you have a bunch of images, and 100 milliseconds later, there's another pattern. But you have all these, the information is there. It's just scrambled up. And so if you take short exposures, then you can use a computer program to unscramble it and use Fourier transforms. Okay, and so with that, so then we thought, well, let's try to get time on a larger telescope. So we put in an observing request to get peak, and this is a 2.1 meter telescope, about the same size as your telescope up here on the summit. And had 2 week-long runs, observed about 1,000 double stars on each. And so we've got it was 10 hours a night, every 4 minutes a new double star, mass production. But there's it was a student effort. This is down on the 100-inch telescope in Mount Wilson, historic 100-inch telescope. Well, the seminar went well, and we were starting to do true cutting-edge science with speckle interferometry. And so we started thinking about how could we expand the seminar. And the idea was, instead of having several teams from one school do a seminar, which was to have teams from a bunch of different schools doing the seminar. So that's what we've been doing for the last several years. And it's kind of, part of it's online and part of it's in person. And I'm kind of the overall instructor, but there's, at different locations, there's support instructors. We've got a textbook now. In fact, let me pass that out. Oh, here it is. So this is the preliminary edition. And we have a website, and we're using primarily robotic telescopes now. We found that the advantage of using robotic telescopes is that they're usually at better sites. It's good weather. Parents don't have to bring their students to some dark site someplace and then come pick them up later. It does have the disadvantage that lots of students really, they want to look through a telescope and operate a telescope and so forth. And so we often arrange for them to do that, but we try to get our science data now mainly through robotic telescopes. And we formed an institute for student astronomical research that kind of helps in the overall process. So we've been doing this. The first year was 2015, so this is our our third year going this approach. And huh, go away. Uh-oh. Yeah, go down. Okay, I can skip through to it. Hello. Well, this is a quick review. The test will follow. We're almost finished. Okay, let's ignore it this time. Okay, so here's the activities. So students learn about scientific research and double stars. Oh, didn't like it. We're near the end. If we can't get it going this time, we'll skip this part of it. I don't think so. You think maybe it was trying to jump to the sound file? Yeah, it could be that maybe the slide was taken from something that had a sound file. Come to the one that shows the all the and go one past that slide. Okay. Hey, control. Yeah. So here's some of the schools that we held it at. And we had one year we had 2 from Hawaii, 6 from California, 1 from Arizona, and 1 from Pennsylvania. And there's Steve with some of the students. So what's happened to some of these students? You know, Steve? And, and this is over at Leeward Community College on Oahu. And so that was, so I had the seminar over there. This is at California Polytechnic State University. And so in the summer, I have a research seminar there. There's the dean of the College of Science and Mathematics. That's Albert there. At any rate, this is uh, in the summer I have a class at Cuesta College, a seminar where we have 30 students, and we actually just have 5 students here. The students at Cuesta College have to pay it. At Cal Poly, they actually pay the students $2,500 to take the research seminar. And 5 students, and they pay me twice as much as they pay me at Cuesta. So it's great deal, and they give me an office. And this is the seminar this year. So this was a photo just a week ago. This is the astronomy professor over there, Mohan. This is Mark Silman, who's the high school principal, and these are all his students. And so, any rate, if you do something here at your school, at the Montessori school, I'll probably get you together with the students over on Oahu. I think it'd be nice to have an inter-island Zoom session on double stars. And so this is actually the last slide. So I want to talk about where the seminar is today. This past September, we just started a grant from the National Science Foundation to kind of evaluate the seminar and expand it to other areas of astronomy. We're moving towards essentially a totally online seminar. Local teams, quite often, that can meet among themselves, but the seminar overall meets online. We've got a conference in June, which you would be almost welcome to in San Diego, about robotic telescopes and student research. And then we have a binary and multiple star conference in Irvine, California, in early August. So if you're keen on binaries, this is the 5th International Conference on Binary and Multiple Stars. The first 4 conferences alternated every 2 years between France and Spain. I went to the 4th one, and we were discussing where should we have the 5th conference, and some wise guy in the audience said, let's hold it in the U.S. right before the total solar eclipse. And the idea being that they can get their universities to pay for them to come to the conference, and they can stay and watch the total solar eclipse. And so they looked at me and said, so at any rate, we're holding it at Concordia University in early August, right before the eclipse. And then, just today, settled JD and I are going to co-chair a conference on student astronomical research here at the Institute for Astronomy in February of next year. And so all you young researchers, get ready to give presentations. You'll be an international conference of professional astronomers, amateurs, and students and educators. And how many people did we have last time, JD, here? It was 40, 45. Yeah, so we'll probably, well, what'll limit us, it'll be the first 45 first serve, right? Because we only got so much room here. And I'm very interested in seeing if we can expand published student research here on the islands. So not just Oahu and Maui, but we try to pick up some folks from the Big Island too. And so we get maybe some things where we're getting some inter-island cooperation. And there is national and international interest in the seminar, so we're working on expanding that out. At any rate, that's the presentation, and I'd be glad to. We have a little bit of time left, Steve? How much? Okay, we don't want to go over time, but we have time for some questions, or we're going to quit early. So anyway, thank you very much. Right, I'll do that. Okay, give me your name first. Trevor. Okay, so Trevor, realizing in the introduction that many decades ago I was a rocket scientist working on actually guidance systems for rockets, wants to know if we should reuse the whole boosters, or okay, the question is, was it more expensive to rebuild than what, put in new ones? Yeah, I actually don't know the answer, but what I think is cool is SpaceX, where you've seen where they have the boosters go up and then they come down and land at a barge at sea. Sometimes it's a crash, but uh, but that's going to make space travel much more economical, I think, if you do that sort of thing. The okay, open to more questions. Yeah, Steve. Yes. So if you go just Google and type in Journal of Double Star Observations, in fact, you can just type in JDSO and it'll come up, and uh, you can look through the papers there. Some of them, it, it's it's actually hard to tell which are student papers and which aren't student papers, because they're all professionally done papers. But if you see my name on a paper, you can. I tend to be just put myself on as the last author. The rule is if you contribute significantly to a paper, you got to be included as a co-author, really whether you want to or not. So like on your paper, if you do a paper at Montessori, uh, you'll be co-authors of it. But if I give you a bunch of help, guess what? I'll be one included as a co-author too. So if you go to the Journal Double Star Observations and they have a you can click on their index and it'll pop up alphabetical all the authors. Or you could do Joe Johnson, the or J.D. Armstrong, or Luke. What's Luke's last name? Luke Jones. Yes. So yes. Question. Ah, excellent question. So yeah. Okay. The question is mass is important, but it essentially, if I understand your question, it's one thing to know what the combined mass of the two stars is. It's another thing to know what the individual absolute mass of each individual star. Is that your question? Yeah. Well, you can get ratios, for instance, on eclipsing binary stars. We talked about transits, and if you have a small star in front of a large star, you can get some idea of the area, and so you can get some idea of ratios. But to get the absolute mass of a star, uh, kind of the approach to do this accurately is you find the combined mass of the two stars using Kepler's third law. You get an orbit doing like we talked about, the kind of data you're gathering. If it's on a binary star, it's adding these points of the orbit, okay? And so you make an observation and it's added to the ones that have been made maybe for 100 years. And you get the orbit, and from the orbit, you get the period, and you can get the semi-major axis as an angle out in the sky. But what you need to know is the physical thing. So you have to know how far it is to the star. There's various ways of getting that. And once you do that, then a real simple trig tells you what the semi-major axis is. Then that gives you the combined mass of the two stars. Now you got to parse this out between the primary star and the secondary star. And one way of doing that is the stars orbit around the common center of gravity. One star is coming towards you, the other star is going away, and it shifts the spectral lines. Come towards you, they shift towards the blue. When it goes away from you, shift towards the red. And so you can develop these curves of the rotational velocity. And when you combine that information with the orbital information, then you're able to actually separate out the mass to the individual stars. And that's very valuable for stellar evolution. Yeah, so uh, some stars, their their orbit is so long that it's just starting to show a little bit of an arc, and so you can't estimate, but the orbits are actually millennia long. We didn't really start observing double stars seriously until William Herschel started his catalog in 1781, and so it's been 17, 18. It's what, like 300 years that we've been observing. So a star that has a period longer than 300 years, we don't have a complete orbit yet. And ones that, and those ones are going to be stars, with long periods. It's hard to get an accurate orbit, and what you really want is stars with shorter periods. So there's always been the pressure to get stars that are closer and closer together as they appear in the sky, so you pick up shorter and shorter orbits. And so uh, uh, with speckle interferometry on the size telescopes, like the 2 meter up here or the 2 meter I was showing, you can get down to about a tenth of an arc second separation on the star, and that'll give you an orbit of the fastest orbits of a couple of years. But then there's telescopes. You get on a 10-meter telescope like Keck at, over on the Big Island. Then you can get down to orbits that are months, and then if you use there's a telescope system on Mount Wilson that has 6 1-meter telescopes that are hundreds of yards apart, and they combine the light from these telescopes to form an interferometer. And with that, they've gotten down to systems with an orbit of just a few days. So they're just really spinning around each other. Yes? Yes, we will. The question is, how would you define a small telescope for astronomical research? The one answer is any telescope less than a meter. But I think in practical terms, a small telescope is one that you can buy at a reasonable price that amateurs buy. And so the amateur telescopes go up to about 14-inch aperture. And you can do useful science with telescopes as small as, like 4 inches, a little 4-inch refractor. And so so that's kind of the range of small telescopes. Small telescopes nowadays are quite powerful instruments because you can couple them with charge-coupled device cameras. Essentially, the same kind of camera you have in your cell phone, although sometimes they're thermoelectrically cooled, and they're much more efficient than film, much more easy to use, and so small telescopes have become powerful research instruments. And so astronomy is kind of broken up into large telescopes. So large telescopes mainly observe distant galaxies and very faint things, while small telescopes observe stars in our galaxy, closer, brighter things. And it's a good division of labor. Some of the telescopes, like Pan-STARRS up here on the summit, does surveys, but you want to do follow-up work with small telescopes. So small telescopes operated by amateurs and by students can make, there's more of them than there are professional astronomers in big telescopes. So the small telescopes and students and amateurs can do follow-up observations. They're very valuable. Yeah, so some of the other research areas that are really good for student projects with small telescopes. Yeah, that's the question, is what are some of these other areas? So one area is there's a bunch of different projects you can do. Instead of in double star astrometry, you essentially take an image or several images, and you're measuring position angles and separations of stars in the image. Another thing you can do is take a series of images over time of something that's changing its brightness. So we talked earlier about how you could have a pulsating star changing its brightness. Well, the pulsation period, if it's uh, 6 hours, you can keep observing it over the 6 hours, draw a brightness curve versus time, and you get this what the pulsation looks like. Or you could have an exoplanet transiting in front of a star, and the exoplanet transit lasts, oh, what, JD, typically 2-3 hours, right? And you maybe want to observe it an hour coming in, 2 or 3 hours across the star, maybe an hour out, so maybe in 5 or 6 hours you can do it. Another good thing to observe is asteroids. So asteroids usually have some strange shape, and they're rotating around. And so as they rotate around, the amount of light that's reflected from the sun changes. And so you can get the rotational period of the asteroid. You can actually start getting some idea of the shape of the asteroid. The problem with these time series ones is unlike the double stars that I mentioned earlier, where you go out and you just get a few images and you're done. Here you got to spend hours at the telescope, and so that's hard to arrange for students. But with robotic telescopes, if you can get the time on the robotic telescopes, then that makes these projects possible. So we're just starting these kind of projects now, and on the way over I was talking with JD about using the 0.4 meters up at Fox Telescope North to actually get some of these time series photometry. Generally, spectroscopy, which takes the light and spreads it out, is a game for larger telescopes. Okay, Preston. Well, exo means what, beyond or outside. So it's, I think it's being outside the solar system or beyond our solar system. So it's a planet that's beyond the solar system. You could call it that, but it probably wouldn't be correct. Okay, well, I want to thank everyone for your time and attention, and if you want to stick around just for informally to talk, that'd be great. I'd be glad to hang around for a few minutes. And thanks. And a little applause for JD and the Institute for hosting it.